like to open with a quote. I read a book the other day about speaking in public, and it said something about opening with a quote. Okay, it wasn't actually a book, it was a web page. It was called Top 10 Things You Should Never Do While Giving a Talk. But I'm going to open with a quote anyway, because this is where it all started. We are about to study the idea of a computational process. Computational processes are abstract beings that inhabit computers. As they evolve, processes manipulate other abstract things called data. The evolution of a process is directed by a pattern of rules called a program. People create programs to direct processes. In effect, we conjure the spirits of the computer with our spells. So when I first read that 2 years ago, it was like something that had been misaligned suddenly snapped into place. And this idea that the code that we write, the artifact that we're creating, and the process that unfurls in the system as that is being evaluated are two separate things. This is so simple. It's such a fundamental idea, but it's so easy to overlook. If our code is directing the evolution of a process, then in many ways it's a lot like the DNA in a cell, directing the evolution of that cell. But DNA is really the most boring part of the cell. It just sits there, curled up into little balls, being read, right? And all around it, there's this fantastic machinery that's involved in finding pieces of the DNA in a massively parallel way and unwrapping it and parsing it and opening it up and copying pieces out of it into RNA, jitting it down, and then that RNA goes out into the rest of the cell and causes effects. Some of it gets pulled into ribosomes, which are these amazing molecular machines that kind of ratchet in a little bit of RNA and sort of poop out a little bit of amino acid at the top. And they find the right amino acids to match that sequence of codons in the RNA, and then they make this protein, which is like a data structure that has active sites. It's like an object in JavaScript, and it causes effects on other things. And we can keep pushing this biological metaphor, but the point is that there's a party going on in there, and we weren't invited. I want to go to that party. So this talk is a series of 3 steps of me trying to find a path to understand what's happening in this process as it's evolving. Step 1 is data. Our data structures in JavaScript are becoming increasingly sophisticated. This is in response to our applications that we're developing becoming increasingly sophisticated. And in particular, there's a lot of complexity that's being added in asynchronous processes. And when we share mutable state between asynchronous processes, we have exactly the same problem that people in other communities have when they share mutable state between threads in a multi-threaded environment, right? So we run into these concurrency concerns because now we've got something over here, thing A, and we've got some other piece of code over here, thing B, and these two things are communicating through some communication channel. They're sending messages back and forth, but if they're also sharing mutable state, then they're communicating through that too. And that communication happens instantly, and it bypasses the communication passageways of your application. So that means you have this spooky action at a distance going on when you're dealing with mutable state, right? And it's all right. So we have persistent data structures that help us have immutable data, so we can reason about our processes and our programs in a more effective fashion. And they do that in a performant way, rather than having to deep copy everything like you would if you were making immutable data yourself. So we're going to look at 2 of those, immutable.js and Mori, from a very particular perspective. So first you need to know a little bit about hash array map tries, or trees. Who says try? Who says tree? Okay, either way is fine, you're both right. As long as people understand what you're saying. I mean, a try, I will try to say try because I think it disambiguates better. But even though I'll try to say try, a try is a tree, so I may say tree. So here's what we're dealing with. This is just a super high-level surface topology of a hash array map trie. They're really interesting data structures. It's a trie, so we put all of our values down at the bottom, and we use pieces of the key to walk down to that value. We're going to hash those keys first so that we can pull an unlimited number of bytes out of them. If we hit the end of the hash, we just rehash. So that gives us consistent hash lengths and also an unlimited hash length. So we can deal with conflicts, because if two things have the same key, or say the same piece of the hash of the key, then we have to go to the next piece of the hash. So we're going to take pieces of the hash 5 bits at a time and use that to walk down this tree. Those 5 bits give us 32 possible values. So we're going to have an array of 32 possible values, up to 32 values, as the child of a particular node, and that's going to dereference into its children. All right, so the things you have to remember from that are 32 and hashing. Hashing gives us good distribution properties. We would rather have shallow, wide trees. We don't want deep trees because depth increases our space usage and also our time usage. So we're going to put these two libraries under a microscope. We're going to use a thing called underscore, which is kind of like a data structure oscilloscope or something. And this is slightly the wrong aspect ratio, so you're not seeing all of the slides. That just says full history of the data structure down there. Okay, so these are the joys of AV confusion. So, which was, my fault, not theirs. They did an excellent job of recovering from that. So we're going to write out our data structure as a single long list, right? We're going to take all of the numbers in it, and for each number in it, we're going to generate a pixel. That pixel will be colored according to that number. We're then going to take that line of pixels, we're going to turn it on its side and make a column. And every time we make a new version of this data structure, we're going to move everything over and put that new column in place so we can see the history of it. So let's cross our fingers and see if we can see what that looks like. Here we are. Oh, man. Aspect ratios. All right. So everything's kind of up in this corner, but that's cool. We can zoom here. This is the power of zoom. All right. So what we've done here is to start putting in some numbers. We see this triangle shape. That's what we're expecting because every single tick we're adding a new number. We're enqueuing a new random number. We see random banding patterns here. Those correlate to the random numbers that we've added. So once we add a number, it just stays in its place in this queue. The secondary feature that we can pick out here is these shaded areas, which are shaded. They're less light because they are down an extra level. So the lightness is corresponding to our depth in the tree. This area is down an extra level, so we can see it fills up with 32 things, and then those get added to the main data structure, and we start a new nursery at that point. Everybody on board so far? So both of these, and I've cleverly codenamed them blue and red, because this is not a performance comparison between Mori and Immutable.js. It's just we're going to use these as a way of understanding what's happening in the process and in the program by looking at the data. Additionally, even if you figure out which is which is not very hard after I hit a couple more buttons, I'm using older versions of them, so it's still not a very effective performance comparison. All right, so what happens if we start taking numbers off? So far, they look exactly the same. Suddenly, we see a really big difference. So over here in the blue zone, we have a data structure that is the same size, right? So here it was growing, and here it's the same size every tick. And what we're doing every single tick is pushing on a number and dequeuing a number off of this end. And we can see that that's actually happening in the data structure, right? There's a couple of strange little places in here, like this little blip here that occurs about 6 ticks in. I have no idea why, but it's there every single time. I haven't looked at the code for either of these. The point is to understand it just by looking at the pictures. So this seems like a fairly straightforward traditional queue, other than the fact that we still have our nurseries going, right? We're shifting off of one end and pushing onto the other end. So there's probably some performance implications here because shift or unshift, whichever one we're using in JavaScript, is not a very fast function. Over here, we're doing something completely different. In particular, we can see that a whole new triangle has emerged, and we're keeping the old data up here. So what we infer from this is that rather than destroying things as we dequeue them, we're keeping pointers. And in fact, we can see those pointers here in this middle section. We're keeping pointers into this data, and we're floating a counter to the end of it as we dequeue things. And then when we hit the end of the old kind of master section or new growth section, we're dropping everything. And this new growth section down here becomes the new old one, and it starts getting dequeued, and we start over again here. Does that kind of make sense so far? So what we understand at this point is that there's a massive difference between these two libraries and how they handle queues. And in particular, there may be some performance implications for that difference. We understand this not by looking at the code, but just by looking at these pictures. Let me show you another example. We're going to start throwing random numbers in here. So we'll take a number and we'll give it a key that is the number with the letter prepended, and we'll insert this into the map. So what do we immediately see when we're looking at this? We immediately see that this blue side is about twice as tall as the red side over here. And so we can start to think that maybe there's some spatial implications here, right? That our space usage is a little bit stronger over here. Let's turn on another way of looking at this. So this is a flattened tree view. What we're going to do is take our tree with all of its levels, and we're going to flatten every single level. And then we're going to turn the whole thing on its side. So if we look over here, we can see that we have our initial node here. This blue is a pointer to the secondary node here. This points to an array of 32 pointers, which each point to a dereference column here. And then those point to this array over here, and so on. But just from eyeballing this, don't know how much of this you can actually see, we can see that these are adding new key value pairs in very different ways. This one is a lot more compact. So this reconfirms our intuition that we saw just from looking at the sizes. Let's try, instead of adding these randomly, adding them, come on, you can do it. All right, apparently the reload button is not actually the reload button. Borrowed laptop issues. All right, what's happening here? Now we're loading in numbers sequentially instead of randomly. And something that we started to see toward the end of this one becomes very clear. We're seeing this banding effect. Whereas these colors are well distributed, these colors are patterned in a very particular way. And what that's telling us, and if we look here, we can see the same story. This one, even though we're adding them sequentially, is well populated. It's fairly dense. Over here, we see something that has these increasing sort of harmonic oscillations that are going on in the number of collisions. So this tells us that the hashing algorithm that blue is using is not distributing values or keys as well as the hashing algorithm that red is using. In fact, we're getting very bad hashing behavior out of this. It's probably modulo or something like that. Oh dear. Fortunately, that was actually the end of the conclusions that we were going to draw from that. So what we've learned so far is that you should always bring a backup laptop when you're giving a talk. And the second thing that we've learned is that we can make observations about a piece of code without ever looking at that code at all. So we've learned something about these two libraries, but we didn't have to look at any code. And that's important because it doesn't matter how good or poorly written that code was. Right? It could be minified, it could be obfuscated. Both of these are well-written libraries. But even if they weren't, we could understand them. And if we can do the same thing that we just did for a library that's producing a data structure, for a library that, for example, is our framework that we're using, or that someone else is using, and suddenly we have to take over maintenance of that code. There's hundreds of thousands of lines in the framework, so we could read the entire thing to understand how it works. Or we could try to go in the back door and develop our intuitions by actually observing the process unfolding. So one problem that we saw, well, I guess we didn't see, but we should have seen, was that there was limited screen real estate. We had the opposite problem. There was way too much screen real estate. So fitting everything in can be an issue. All right. I will. Sorry? Will that actually work with images? It works. That's so great. Thank you. Cool. So we have some issues with the amount of available space to us. So we could, for example, look at a single line of code and observe this line of code, or we could observe the entire code base, right, and watch the entire process unfolding. So we can kind of pick a place along this continuum that we're interested in. We could also, on the temporal dimension, look at a single operation at a time, or we could look at the entire process unfolding in real time. And so we have really good tools for this end of the spectrum, for looking at a single operation one at a time, right? Step-through debuggers work great for this. And they give us a street-level view of what's happening, right? We're walking through the town of our process, but they don't give us the 10,000-foot view of what's happening all at once, so we can develop our intuitions about it. And we don't have very good tools for that right now. So that's what's on the left hand of the slide. On the right hand of the slide is some mathematics that ostensibly proves that the information we would like to have is greater than the information that we actually have, but really it's just a ham-handed way of trying to work the 80s theme into my presentation. All right. So what we're going to do, because JavaScript is huge, the ES5 spec is over 250 pages, and because we write huge applications in it, we're going to punt a little on this problem. And we're going to start with a system where we can see everything at full granularity, but the entire process all at the same time. Okay? So that means we're going to have to design a language. We have some design constraints for this. We'd like to keep it very simple. So we're going to have an 8-bit architecture. Our memory is going to be 256 bytes. And we would like to introduce random programs, because the whole idea is to gain intuition about the process that's unfolding from a program without actually understanding the program. If we understand the program, then we don't need to do that, right? So we need random programs. That means we're going to fuzz the compiler. We'd like there to not be any compile time errors when we do this. We'd like there to not be any runtime errors. And I'll throw in an additional constraint that we want all of our programs to terminate. So this sounds easy, right? Sure. Oh my gosh. It's so tiny. Woo! All right, so here is a program in our language, and this over on the right is supposed to be the JSConf Pegasus, but my pixel art skills are not very good. It looks more like a flying aardvark with a Tommy gun or something. All right, so if we run this, we can see that it's some type of image blurring program. And just so you know that really? Okay. No. Did I get bounced off the subnet? Is that why I can't refresh? Thank you. Okay. So I was going to show you that we could edit the program and it would still work. You'll have to take my word for that. It's the magic of live demos. That's great, but we're not seeing individual steps. So we want to go back and be able to actually see things at a granular level. So now we can see the stack, we can see the return stack. These are the two, this is the entire process unfolding. We see the memory, we see the code, we see where we're at in the code thanks to this highlight, and we see the full variable structure right here. So this is everything. If we took a picture of this, we could replicate this process at this moment perfectly, and we can step through and see that it is in fact doing some things as we step through. But in zooming into this level, we've lost our ability to see things unfold in real time. So now we're back to the step through debugger zone. So what we can do is we have a connection between code, which when it gets compiled down, all of these opcodes over here or these commands over here get pushed down into numbers. So we can actually make an array of numbers out of our code, and that's exactly what happens. It gets compiled down to a machine code, which is an array of bytes. So at the machine code level, we have an array of bytes, and our memory is an array of bytes. So we have a sort of trivial form of homoiconicity, which is where your code and your data are the same thing, right? In a Lispy language, you get a more advanced form where you're writing in the abstract syntax tree, and that's the same type of data structure as the data structure that you typically operate on. Machine code always has a trivial form of homoiconicity, but in our case, we have a secondary trick up our sleeves, which is that our memory is being mapped to an image. So there's actually an isomorphism between the memory structure and the image. And so there's also an isomorphism between the code and an image or icon. So maybe our homoiconicity is not so trivial after all. That was a really involved joke. All right. So we can look at this as an image instead, which is where things start to get fun. So this is our program running. Again, we could take the snapshot and reform our entire process at a moment in time. You can see the read head is this kind of white square here that's jumping through this subroutine. And you can see that it is, in fact, performing this image blur on our memory. So that's great, but what we're really interested in is random programs. Oh, and I can't reload this, and it's stuck in a really silly loop. Are we good? Yes, nice. Okay, so we're watching an entirely random program. All the color spots correlate to different types of opcodes. This is an exit, so it's the beginning of this subroutine, and this is a jump, so it's jumping to the next subroutine when it hits that. The grayer areas correlate to numbers that serve as constants in our program. And what can we infer about this? Well, it's actually hard to infer much of anything from this system. We can see that this square is blinking a lot, and that we're going to take a little while before we end because we've got 200 counting down on our return stack. So what we're doing here is we're applying the program to itself. We put a copy of it in memory, and we have it modify itself. And then when it's done, when it terminates, we're going to take the modified version and run that against itself. And we're going to keep doing this until our program doesn't do anything interesting. Well, this one is certainly doing something interesting down here, at least. Or we find a cycle where a program A applied to A gives us a program B, which when applied to B gives us a program A again. And then we would be very happy and have champagne or something. All right. So this was a nice experiment, but it's a little hard to infer much about these programs because the language is a little obscure and because we haven't looked at these pictures long enough. What if we could do this with JavaScript? That's the $25,000 question. So what if we could look at the interpreter for this in JavaScript? So I was hoping to not have to do this, but I have to do this. All right. So we'll take this over here, and we will do this, and we will do this. Oh, good. Okay. All right, everyone cross your fingers, take a deep breath, and we'll see if we can make this work. All right. So what we'd like to see is our virtual machine for this little language that we've written running in real time in JavaScript. And over on the left, that's exactly what we're seeing. So we're back to the step through on the right. We're stepping through one step at a time. But as we step through, we're seeing 3 columns over here, which correlate to 3 files. This is the core virtual machine. This is the renderer. And this is the index.html. Can you see that? Can anyone see that at all? You can? It's visible? Okay, cool. Okay, so as we step through, there's going to be lots of flashing colors here. We can see different parts of this program being evaluated. So this is the actual underlying virtual machine. This, for example, is the draw function. And it's longer than you would expect, and it's also very, very hot. So this is forming a heat map because there's a tiny little virtual DOM inside here, so I just call it like 256 times a tick. But the point of this isn't to be a profiler, right? We already have really good profilers for finding hotspots in our code. The point of this is to, at a 10,000-foot view, understand the process that's unfolding from our code. And so another interesting thing that we can do is not just watch this in real time, which we can do a little more effectively if we speed this up. We can also slow it down and watch it happening essentially a tick at a time. So we can see the process, we can see the underlying engine kind of flowing through. And unfortunately, this code is not very interesting because it's calling the draw function 256 times. But we can rewind and try to, we can rewind. Okay, maybe we can rewind. We can't rewind. Really? Okay. So this isn't very interesting for me, this particular piece of code, because I wrote it. So I understand exactly what's happening here. If we look at something else, though, something bigger, like, for example, a framework of some kind that we're not familiar with. This one is Agility.js. And then if we do this magical thing that may or may not work, okay, good. So I'm using Fondue under the hood, which is an instrumentation library written for Theseus, which is a debugger for brackets. Typing and talking simultaneously are surprisingly difficult things to do well. Okay, flashy lights, woo! All right, so what are we really looking at here? What we're seeing unfold before us is the entire process that's inside of Agility.js as it's handling the things that we've clicked over here. So if we click this, for example, come on. And then no, we can't rewind. All right, so I should slow this down a little. Okay, so we can observe at a high level the functions that are being called and the flow of functions as they're being called. So this shows us something about the process, and we can draw some inference from it. But there's more that we need. What we'd really like to see is the data that's flowing through here as well. And we'd like those data flow pathways to be highlighted. We want to be able to sort of pour data in some input of our program and watch as it trickles through the function calls and invocations. And watch it when it pools up in some place and stays there for a while, see how it interfaces with other data that's flowing through. We want to be able to understand the applications that we're working with at the level of the process that they're evolving. And we want this because reading code is very slow, and it requires that we have an interpreter in our head. And if we can do this effectively, then we can understand, for example, frameworks that we've never used at an intuitive level without ever having actually used them or read through their code or documentation. So I want this for the programs that I'm writing, and I also want it for the programs that I'm reading. And if you want it too, then I think we should work together on this. I think we should make this happen. I think we should get this, not this, but something like this, into dev tools, right? So we have it available for everything that we're doing. Let's augment our vision. Let's let the computer do the hard work of helping us understand what it is we're working with. Let's go to that party. Thank you.